Hello everyone, welcome to this first video on group theory. I'm doing this video because when I first approached to my group theory course, despite I had the most amazing professor who made me love this branch of mathematics to death, it was really confusing. I was coming from very little theoretical mathematics, and I didn't know, I barely knew what I was asked for. So I will call this video a survival guide for confused abstract algebra group theory beginner. So I hope this will be a help, and let's dive into the math. Okay, so group theory. The first thing we have to do is we have to define a group. Before that, we need to know what is a binary operation. Okay, a binary. I'm gonna state definitions, and then I'm gonna explain it better after. Okay. A binary operation on a non-empty set S is a function that maps each pair of element of S to an element of S. Okay, so we have a set S that is non-empty, and we have an operation that we call a star. Okay, so for if A and B are element of S, then star of AB is equal to AB, which is also an element of the set. What is this saying? If we have a set, and we have an operation. Imagine an operation, any operation you want. It can be multiplication, addition modulo n, multiplication modulo n. It can be matrix multiplication, matrix addition. Okay, any of them. Imagine one of them. Okay, so we have a set, we have an operation. Take two elements of the set, operate them together. If the result is in S, we have what it's called the closure property. Okay, so basically we operate, this operation allows us to operate within the set, and the operation is binary. Okay, so we have our binary operation. Again, this operation allows us to stay within the set, and we have a very important properties we'll have to check it all the time, which is called closure. I'll get back to that later. Okay, so we have a binary operation. Now we can define a group. A little more space. Okay, so a group. Okay, get a set, call it G, and let this group G be a non-empty set equipped with an operation. Okay, so with a binary operation. So we call a star, and on G this operation preserves the closure property. So this operation allows us to operate within G. Okay, so we have this group, we have this set, and we have this binary operation. Okay, then G is a group if under this operation the following properties are satisfied. Okay, very important. Now we're going to see what these properties are. Okay, but let's stop here already. A group is a non-empty set equipped with an operation, okay, that satisfies some properties. So a set is not a group, okay? A group needs a set, it needs an operation, and within, if we operate this, if we operate the elements of the set with this operation, then we satisfies the properties, okay? Sometimes I hear questions like, is the set of real numbers a group? Well, this question is not complete. It is missing the last part, okay? It doesn't make sense. What makes sense is the set of the real number under multiplication a group? This makes sense, okay? So a group is a set and an operation, okay? Not only a group is a set with an operation, and these properties, these three properties, are satisfied. The first property is associativity. Activity. Okay, what is it is what you guessed, is the same as of the regular addition and multiplication associativity. Okay, so if we have three elements, we call it A, B, and C, that are in the set G. Obviously, we use this is our operation. Then A star B star C must be equal to A star, or A operated with B operated with C. Okay? If this is true, then we have the associativity property. The second property is the identity. Okay. This property states that there must exist an element we call E in the group G, such that for all elements of the set G, we have that A operated with E must be equal to E operated with A and must be equal A. Okay, so every group needs an element that is, let's say, between us, that is neutral, okay? Doesn't do anything to the other elements. A operated with E is A. In addition, we call this element 0, because if A is a real number, so, and under addition, the identity is 0, because any real number A plus 0 is A. And in multiplication, the identity is 1. A times 1 is A. And matrix addition is the matrix with all the entries are 0, and so on. Okay, so this is the second property. Now we have the third last property. We have the inverses, and it says that for all elements of the group G, for all elements arbitrarily called A and G, there exists a unique, the symbol, the exclamation mark means unique, a unique element B in the set, such that A operated with B is equal to B operated with A, which is equal to E. Okay, the same of the inverse of that we might have an intuition of how an inverse, the inverses of the real number under multiplication can be, so is the reciprocal basically, right? So if m is a real number, then 1 over m is the inverse, because m operator, so times 1 over m is equal 1, which is the identity. Okay, so we have these three properties. Let's recap. So what is a group? We have a set. The set is kept with a binary operation. Okay, so again, you have the set and an operation that allow us to operate the elements and staying within the set. Okay, and not only this, but under this operation, so operating the elements, we can use the associativity property. We have an identity. In the set there is the element that works as an identity, and each element, so all of them, has to have an inverse, such that the element operated with inverse gives the identity. Okay, if there's one element, only one element in the set that does not have an inverse, then the set is not a group. Okay, let's see if we can find some examples of groups. Okay, let's do this. Okay, first example, the set of the real numbers, let's do this, equipped with addition. Okay, let's think about it. We said that this operation must be a binary operation. Okay, so we need to have the closure property. So there are three main properties to check of the group, but in reality, in order to prove that a set equipped with an operation is a group, there are four things that we have to check, and they are closure, associativity, again identity, inverse. Okay, this comes from the operation being a binary operation, but is a condition that is necessary. Okay, so we have to check that. Now let's check all this for this group equipped with this operation. So the set of the real numbers with addition. Okay, do we have closure? Is there any instances where I add two real numbers and my resulting element is not a real number? Well, no, there's no such thing. So we can put a check mark on closure. Associativity. We know that the regular addition is associative. Okay, let's real numbers a, b, and c. A plus b plus c is equal, obviously, to a plus b plus c. Okay, so we have another check mark over here. The identity under addition, we said before, is 0. Any element times 0 is that element. So we can check over here. The inverses was if m is a real number, okay, then the inverse is negative m, right? Because m plus negative m is equal to 0, which is the identity. So yes, we check them all, and the set of the real numbers equipped with addition is indeed a group. Okay, let's give another example. How about the set of the integers under multiplication? let's do it this way. This means the set of all the integers under multiplication. Okay. Remember, if one of the properties is not satisfied, then this is not a group. So, or either we check them all, we prove them all, or we give a counterexample for one. Okay. So, how about if an integer, okay, what integer multiply with another integer gives me 1 if a and b are not 1. Okay, we're talking about integers, so they do not have any, we're not in the realm of the rational numbers. So for instance, 3b equal 1. In the integers, what integer b satisfies this equation? None. Okay, nothing. So the integers under multiplication do not have inverses. So this is not a group. Not a group. One more. The set. Let's make this is a little. This is an interesting thing. Okay. The real numbers, the non-zero real numbers, this symbol means that you get all the real numbers but 0, okay, under multiplication. Okay. Yes, without writing them all, without giving too many, without writing too much, we can see that okay, we multiply real numbers, we get real numbers. So the closure, we have closure. We know that the multiplication is associative. Then the identity is 1 on the multiplication, and we know that they all have inverses. Okay, so every element of the set, so the real set, except from 0, they have, if m is in R, then we know that 1 over m is in R, and they're the reciprocal of each other. So m times 1 over m equal 1, and we had the inverses. Okay, but how about this? The set of the real numbers under multiplication. Is this a group? Well, the only difference here is this set contains 0, 2. Okay, however, what real number b satisfies this? Okay, nothing. There's no real numbers that satisfies this. It means that the 0 doesn't have an inverse. Okay, is we're looking for the inverse of 0. So the element that multiplied by 0 gives me the identity, which is 1. Okay, so this not a group. All right, so let's make another example, a little more interesting example, so we get familiar with some of the most used groups. Okay, so this called GL2R. Okay, this called general linear is the group of the 2x2 matrices with real entries and for which the determinant is not 0. Okay, so let's write it down more formally. So it's the set of all the 2x2 matrices A, B, C, D, such that the entries C, D are real numbers and the determinant is not 0. So A, B minus BC, it is not 0. Okay, remember that this is the determinant. This is the determinant. Okay, Let's see if we can prove that this is indeed a group. Okay, I'm gonna do all the calculations, but I believe that you already know what to do. So we have to check 4 things. Remember, I'm gonna write it down because it helped me all the time when I was at the beginning to write them all down, because I used to forget to check one of them, and if you forget one, then you didn't prove it. Okay, so we have closure, we have associativity, we have identity, and inverses. Okay, closure. So the operation, let's say A1 B1 C1 D1 times A2 B2 C2 D2 is equal to, okay, we have A1 times A2 A1 A2 plus B1 C2. I'm just multiplying the matrices, okay? Then this entry we have C1 A2 plus D1 C2, and here we have A1 B2 plus B1 D2. This is not even so important, but the point is that all this ended up being real numbers, right? So here we have C1 B2 plus D1 D2. Okay, obviously these are real numbers. Okay, we know that if we multiply real numbers, we get real numbers. Real number plus real number is a real number, all of them. So all the entries are real numbers. So okay, let me pause a second. We want, if we multiply two matrices, we're checking closures, right? So if we multiply two matrices, because the operation that our set is equipped with is matrix multiplication, okay? If we multiply two matrices, we need the entries to be real numbers and the determinant be not zero, okay? And let me make a quick note. I didn't specify, and was my fault, I did not specify that this group implies matrix multiplication as operation. I'll give you a list at the end of the most used groups, okay? So, and I don't know, by conventions we just do not state what's the operation because it's implied, okay? So they already checked and we know that they are groups. I'm going to make you a list at the end. Okay, so remember that the determinant, if we have two matrices A and B are matrices, then the determinant of AB is the determinant of A times the determinant of B. Okay, we know that since this is in a group, the determinant is not zero. This is in a group. This is in a set, so the determinant is not zero. This is in a set, so the determinant is not zero. This number is not zero. This is not zero. And this number is not zero. If you multiply them together, you get something that is not zero. Okay? So we have closure. Let me go through this again. We have this set, which is the set of all the 2 by 2 matrices. with real entries and the determinant not 0, okay, equipped with matrix multiplication. So to check closure, we need to check if I multiply two matrices and I'm still in a set. And it turned out that yes, we are still in a set, because if I multiply this, I get that, and all the entries are real, and by this law, I get that the determinant is also not 0. So I satisfy all the everything that makes me stay in the group. So the first properties is satisfied, closure. Now for associativity, I hope that you can check on your own that if I have three matrices, A, B, and C are matrices, 2 by 2 matrices, then A, B times C is going to be equal A times BC. And to do so, just add another matrix, and A3, B3, C3, D3, and if you do it straightforward, you're going to see that these two things are equal. So it's very, it's a little long to do it. I'm going to skip it, and I believe you can do it. So associativity is checked. Let's check it over here. Okay. The group is associative. The set is associative under the operation. Now we have the identity. This is very easy, because we already have what we call the identity matrix, which is for any matrix A, B, C, D with real entries. If you multiply by the identity element, then you get A, B, C, D. So we also have an identity, and now we have to check if we have an inverse, and if each element has an inverse, then the group GLR2 is a group. Okay. Note that the inverse, so if we have a matrix A, which A, B, C, D, okay, then the inverse is equal 1 over the determinant, right? The determinant of A times the matrix D minus B minus C and A. Okay. The only conditions that that does not allow this to be possible is if the determinant of A is 0, right? So if this is 0, then the matrix A does not have an inverse. But we already know that we are talking about matrices with the determinant. This is the determinant, right? It is not 0. So since this is not 0, then each element has an inverse. Sorry. Okay, we can check that, and we're good. So we know that GL2R is indeed a group. Okay. Okay, note this. If I only had the set of all the 2 by 2 matrices, would this be a group? Well, we had an argument here, right? That says that this must be the determinant of A. This must be defined. So if the determinant of A is 0, that is not. If I'm only if I don't make any restrictions on my set, and my set is the set of all the 2 by 2 matrices, then there is at least one of them where determinant is 0, okay, and is where see here, yeah, if AD is equal to BC, then the determinant is 0. So if this happens, then that matrix doesn't have an inverse. So the set of all the 2 by 2 matrices under matrix multiplication, it is not a group. Now let's do maybe one more example. After that, I'm gonna maybe go through some problems. Okay, we have the set which is called special linear, okay, of 2 by 2 matrices with any kind of entries. So the entries F can be the set of the integers, of the real numbers, of the complex numbers, okay, so which is equal to the set of the 2 by 2 matrices A, B, C, D, such that A, B, C, D is in F, and the determinant is 1. Okay, is this a group? I told you this F can be any set we want, even some restricted set, like the set of the all the integers less than 5. Okay, so this is indeed a group, because all the first three properties come straight from the one we already had. Okay, and from this one, from the GL, from the general linear, you can find the closure property by multiplying 2 matrices, and this is works for the other one also. Sorry, actually I'm making an argument here. We know that we have closure. We also had the determinant 1. Okay, we said that A and B are matrices, 2 by 2 matrices. Then the determinant of AB is equal to the determinant of A times the determinant of B, which is 1 times 1 equal 1. So here we have closure. We have associativity, just do it. We have the identity matrix as our identity, and also the inverse is just, look at this. If the determinant is 1, then A inverse is D negative B negative CA. Okay. Then the inverse of A is equal basically 1 times D negative B negative C NA. So this also a group that always implies matrix multiplication. Now let me give you just a list of the groups that you're going to use many times, and you have to know they're not going to state what operations is equipped with the set, so just remember this. Okay, if you see Z, so the set of integers is always equipped with addition. Okay, if you see the set of the positive rational number is equipped with multiplication. this is the set of the integers less than n, and is equipped with addition modulo n. The set of the non-zero real numbers is equipped with multiplication, and then we saw that we have general linear to R is matrix multiplication. Then we have the group UN. This is the set of all integers less than n and coprime with n. It is equipped with multiplication. Multiplication modulo n. N. Then we have, I wish I wrote a little smaller so they could all fit. We have Rn, and is equipped with component-wise addition. So we have the elements of Rn are A1, A2, A3, A4, and you have another one that is B1, B2, B3. So the elements are if you combine them, component-wise addition, you have something that look like A1 plus B1, comma A2 plus B2, comma This is our n. We saw that we have special linear to F, matrix multiplication. Okay, let's stop here. These are very, let's call it famous. These are famous groups, so there is no need to specify the operations that the set is equipped with. Okay, but remember this, because you're gonna find some problems where we implies this. Okay, so when one example can be proved that Zn is a group. Okay, this is implicit, implies that Zn is equipped with addition modulo n. Okay, or with all the same. Okay, so only for this. If it's another group, usually they specify it, but this no, so just try to remember them. They're used all the time and they're already proven to be groups. Okay, I hope this was helpful and it clarified some points. For me, maybe were a little foggy at the beginning. There's another point that I want to make, that at first we start, I don't know why, but they all start by showing group theory by using the symmetries of geometrical figures, and that really confused me a lot, because I came from algebraic expressions and throw into a different discipline by using something that I was not familiar with. Okay, so again, I hope this helped. I'll see you in the next video when I'll solve some problems. Thank you for watching.